TI 8502, U.S. Army Corps Engineering, Railroad Rehabilitation and Design, AFMAN 321125 1 March 2000, Kemp E. Chapter 3, Establishing Route and Profile and Alignment Specifications. 1. Introduction. The production outline in the chapter, along with the information, locomotive propulsion forces, desired train capacity, propulsion, resistance, and the train operation requirements can be used to select the maximum grade curvature, minimum transition between the grades, and reverse curves. Initially, these specifications should be treated only as guidelines, and analysis of the route topographically may require changes to keeping construction costs within acceptable limits. Typical information procedures described in the chapter will be used interrelatively with the Chapter 4 until suitable compromise is reached. C. The Appendix B gives the sample problem illustrating and determining of a ruling grade. D. The specification listed in the chapter are primarily for main running tracks. Chapter 8 gives the additional profile alignment specifications for terminal areas. Paragraph 2 and 3 of the Chapter 6 detail final layout of the horizontal, vertical, and curves. 2. Grades and grade resistance. Definition: railroad grade is designed by the amount of the elevation changing in 100 feet of the length expressed in percentage of the additional forces to move the train due to the presence of the grade is known as the grade resistance. The grade resistance is equal to 20 pounds from each of the ton of the train weight percentage of the grade. This takes the force to pull the train to 2% of the grade as does to 1% of the grade. For the reason that those choices maximum gradient, the rate of elevation of change on a particular grade can have a great effect on the operations over the route. B. The ruling grade. The particular grade of the limiting train size speed over the route. The grade known as the ruling grade. The ruling grade is known also as the steepest grade. A train's momentum may help carry it over the grade steeper but shorter than regular ruling grade. See the grade design categories. Table 3.1 lists the design of the categories for the main running track. Table 3.1 grade design categories for main running track. A 0.0 to 0.4 is percent is a light grade. A 0.4 to 1% is a moderate. A 1.0 to 2.0 is a steep. A 1.5 suggested limiting running grades or 2. To 3 is very steep to be avoided if possible. Through the route profile transition between the grades. Profile and the grade length. The route profile is characterized by the steepness of the grade change in the grade along with the route. The train operator enhanced with the frequent changes between ascending and descending of the grades. Route design and the construction often simplified, avoiding the frequent changes in the grade steepness. Table 32 shows the recommended minimum grade length. Maximum speed of 15 miles per hour or less between the different ascending and descending grades of a minimum grade length of 500 feet between the ascending descending grades of 1,000 feet. Above 1,500, maximum speed above 50 miles an hour between the different ascending and descending grades of 1,000 and between ascending and descending grades of 1,500 feet. B. The transition between the grades. Transitions between the grades are made of the vertical courses. These transitions are necessary for the smooth train operation. They increase the amount of surveying and staking required in more than difficult construction for the uniform grades. 2. The design guidance and the grade transition is given in paragraph 2b of the chapter 7. 4. The curvature and the curve resistance effective grade. Minimum curvature. In general, the sharp curves require more maintenance than the grade curves that experience more rail side wear and gauge widening. They also create a more propulsion resistance. Thus, long-term benefits are gained, minimizing curvature en route. Curvature design categories. Table 3.3 shows the design categories for a main running track. The curve design categories for a main running track. A 0 to 3 degree curve is gradual. 3 to 6 is moderate. 4 is a preferred limit, especially when speeding exceeds 15 miles an hour. 6 to 8 is sharp, and 8 maximum allowable where speeds must not exceed 10 miles an hour. 10 maximum allowable speeds where they must not exceed 10 miles an hour. Combining curves. When designing a route, changing the direction should be accomplished with a uniform possibility, avoiding the series of curves connected by the short tangent. When the two distant adjacent curves of the same direction is less than 300 feet, try combining two curves into one long curve on smaller degrees. Combining closely, the curves usually provides an advantage to less design work, either construction or reduce long-term track maintenance. A preferred alignment single curve is using two curves instead is in the combined curves of the 205 and 200 and 250 feet. The curve resistance is the curve adds the propulsion resistance at the average rate of 0.8 pounds for each ton on the train weight and at each degree of the curve. As a 1% grade adds a resistance of 20 pounds per ton at 1 degree curve is equivalent in resistance to 0.04% grade. Curve compensation. When laying out the route, the additional resistance is due to the curve to be counted with the design. The procedure is known as the curve compensation. Compensation as a grade of the curvature is also required. If the ruling grade is recommended in the grade, it's in moderate higher categories. Curve compensation is sometimes omitted when the curves are very short and gradual degree. When curve compensation needs a grade of curve to be, will reduce the following. GR, the amount of the grade reduction percentage, is equal to 0.04 times the degree of the curvature, decimal in degrees. Actual effective effort, Table 3 through 4. Table 3-4 illustrates the compensation of 1% grade shown in the train values of the long curve of 4 degrees on a 1% grade uncompensated combined resistance equal to 1.16% grade. To maintain effective grade experience on the train, 1% of the actual grade constructed through the 4th degree curve must be limited to 0.84%. Since the actual grade is reduced and compensating curvature requires longer train length and reach in the given elevation. Table 3-4 shows the curve compensation for a 1% grade. Degrees curve 1 through 6. The actuals of an uncompensated grade from degree curve 1 through 6 is 1.0. Each degree gains a 400 of a percent grade. Wait. 400ths, like 104, 108, 112, 116, 120, 124. Remember that way, 4%, and the actual grade is a reduction times the degree of the curve times the 4%. Is the actual compensated grade and effective 1% grade. 5. Locomotive tonnage rating. Definition of the maximum weight of the locomotive is capable of pulling over the route of the tonnage rating. The tonnage ratings are effective main factors, but locomotive traffic effort, ruling gradient among the most important application of the procedure is estimating the locomotive traffic effort tonnage rating as a percentage of the simplified variance intended for the route design purposes. They are not intended to use the actual makeup of the dispatching of the trains. 1. The tonnage requirements of locomotive assignments and the effect of the route on the route design. The route may be designed to allow train sufficient size to travel over the finished line. Maximum train size is determined by the primarily usable locomotive traffic effort of the gradients in the curve along the line. Designers must verify the tonnage requirements with the appropriate transportation officer, as well as understanding general operation plan for the routine traffic training, exercise, and mobilization. 4. On the military railroads, when the government-owned and operated engines are used, the engines must be handled all routine traffic during the train exercise mobilization. Commercial engine may be expected to handle over-the-road operations when installation engine takes care of the switching and short moves and any other operation options. When the installation have more than one engine is used, the two engine maximum tonnage trainage which single train movements are required. This, in addition to the tonnage requirements, plans for the locomotive use must also be known. C. The determining the locomotive tractive effort. Locomotive capability. The traffic effort available for the locomotives to be used on the line tonnage rating should be based on these curves. Otherwise, tractive efforts may be sufficiently estimated with an expression in Table 3.5. Table 3.5, estimated traction effort expressions. The speed range is in the tracted effort. The speed range starting to 10 miles an hour is traction effort of 30 times the horsepower. Over 10 miles an hour is traction effort is 300 times the horsepower divided by the traveling speed of the miles per hour. Because you had it at 10th place. 2. The adhesion limited regardless of the locomotive power. Usable traction effort always limited to the wheel derailability. Adhesion for the design usable locomotive effort. The effort should not be exceeded W4 or the weight of the locomotive in pounds divided by 4. Determining the tonnage rating. When the tonnage rating commonly given to the gross rent trailing tons, the total weight of the cars, the convenient piece of the express tonnage rating is number of the load of the cars the locomotive can pull using the average representative car load of the estimating purpose. This is done using the equation 3.2 along the table 3.6 selecting design car gross weight based on nominal carrying capacity. The number of cars the locomotive can pull is equal to the traction effort divided by in the percentage of grades, maximum ascending gradient length among the containing the whole train percent times 20 divided by the gross weight of the representative car by tons for the table 3.7 plus 3 or sorry the maximum ascending grading length long enough to contain the whole train times 20 plus 3 gross weighting of the representative car tables times 3. The constant 3 and 20 in the equation 3.2 indicates the average car has a rolling resistance of 3 pounds for each ton of the gross weight. All the equipment requires 20 pounds to lift each ton of the weight up each a percent of the grades. A curvature of the maximum grade is assumed to be grade compensated as described in paragraph 4, chapter 3. The grade is equal to the traction effort divided by 20 with the inside parentheses of weight of the engine, weight of the number of the cars by the weight of the gross, number of the cars by the times the weight of the gross plus the weight of the engine divided by times 20 divided by traction effort and 0.15. Table 3.6 design of gross car weights. Nominal car capacity of 70 tons has design gross weight of 105 tons. The design nominal car capacity of 80 tons has a design gross weight of 115 tons. Nominal car capacity of 90 has 125 design gross weight tons. A nominal car capacity of 100 tons, design gross weight of 135 pounds. 35 tons, sorry. A nominal car capacity of tons of 120 tons has a design gross weight of 160. And a nominal car capacity of 140 has a design gross weight of 190. Note that 140 tons nominal capacity represents the carrying of the two M1 tanks. For the field check of the car capacity, normally stenciled on each side of the car as pounds, label the capacity. For example, making a 70-ton car would appear as a capacity as 1,400, 140,000, or else 140,000. Trailing ruling grade. A trailing percentage of ruling grade is determined guided to the first stage of the route selection using the equation 3.3. A 0.15 constant is equation indicates the average rolling resistance for each car, the equivalent to the pulling power of the addition of 0.15% on the grade. The grade length is the effective railway graduate percent, while the grade length is equal to greater than the train length. The traction over the weight of the engine, the nominal number of cars times the weight of the gross, times 20 times the constant in the equation of the average rolling resistance of each car, minus all car curvatures with the limits of ruling grade should be compensated as described in paragraph 4 of chapter 3. A ruling grade is steeper and shorter, and calculated running grade can be used as a total train resistant cars if the grade of the car is off grade does not exceed unusable tractive efforts. Chapter 4 Route Selection.